Hello, Chem 105 students, and welcome to our second and final video for this week. This is going to be about chemical equilibrium. Chemical equilibrium is a process where two opposing chemical reactions are occurring simultaneously at the same rate. Up until now, we've been behaving as if reactions can only go in the forward direction, from making reactants until all the reactants are used up and they are all turned into products. Real chemical reactions often don't work this way. What happens is reactants will begin to produce products, but then the reaction will begin to slow down because, we learned in the last lecture, the smaller the concentration of reactants, the slower the reaction goes. So as this reaction is occurring, the reactants are getting used up, and the reaction is slowing down and slowing down. And then we're creating products, and those products can actually go backwards and turn back into the reactants. And the more of them we have, the greater the speed at which they will go backwards and turn back into the reactants. And there's going to be a certain point at which the speed at which the reaction is going in the forward direction is going to be the same as the speed at which the reaction is going in the reverse direction. And at that point, we will be at what's known as chemical equilibrium. So let's give an example of an equilibrium that is not chemical. So let's say you're this guy here, and you're in a boat, but you find out that your boat has a hole in it. And so you begin to take a bucket you happen to have with you and take the water and start to dump it out of the boat so that your boat will stay afloat. In order to stay afloat, what you're going to have to do is dump the water fast enough so that it's getting dumped out of the boat at the same speed at which it's flowing into the hole in the boat. And if you do that, the water level in the boat will stay even. And so what you can see here is that when this occurs, does that mean water has stopped flowing from the lake out into the boat through the hole in the boat? No, that's still happening. Does it mean you are no longer dumping water out of the boat? No, you're still dumping water out of the boat. What's going on is that the water is flowing through into the hole at the same speed that you are dumping it out. And so the dumping is still happening, the flowing of the water through the hole is still happening. However, the level of water in the boat is not changing, it's staying the same. That is an equilibrium. And we say the equilibrium is dynamic because the flowing of the water is still happening, the dumping of the water out is still happening. So everything's still going on. However, the level of the water in the boat is staying the same because the flowing of the water into the boat and the dumping of the water out of the boat is happening at the same rate. And so similar thing can happen to a chemical reaction. So for example, in the atmosphere, oxygen molecules react with themselves in order to produce O3, which is also known as ozone. And ozone is a molecule that is very, very low in concentration in the air. It's only about 2 times 10 to the minus 27% of the air. It's a very, very small amount of the air. But a small amount of ozone is always being produced from oxygen. Just the speed at which this occurs in the forward direction is quite slow. So once there's a little bit of ozone in the air, now it can go and decompose and go backwards and turn into oxygen. And notice that here for equilibrium, we use this double-headed arrow, or often it's written like this. This is to say that the reaction is going in both the forward and the reverse directions at the same speed. That's equilibrium, right? And so this is indicating the reaction going in both directions, forward and backwards. So O2 is elemental oxygen. It's about 16% of the air. When the rate of the conversion of oxygen into ozone is equal to the rate of the conversion of ozone back into oxygen, then we're at equilibrium. And that equilibrium occurs when there's a lot more O2. So in the air, there's way, 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 way more O2 in the air at any one time than ozone. However, there's always some ozone being formed very slowly, and there's always some ozone getting turned back into oxygen. There's not a whole lot of it, but sometimes it will go backwards. And the percentage of oxygen relative to ozone will remain the entire time because this is an equilibrium. And it's very fortunate that this occurs because ozone will actually absorb UV radiation from the sun, and that will convert it back to oxygen. And so when it does that, it protects us from some of the sun's UV radiation rays, which can do damage to our DNA and cause mutations and cancer in our skin. And so, although there's not a lot of products being formed, this reaction does go forward. It goes forward all the time, but it's also going backwards and using up any ozone that's being produced. So, at any one given time, there's a very small amount of ozone, but there's always some. So, let's talk about equilibrium in a couple of ways. So, on the left axis here, we have a graph. This is describing a reaction, and this is describing the rate that a reaction is going forward. So for example, in this case, the O2 producing the ozone is the reaction going forward versus the rate at which the reaction is going backwards, which would be, the ozone going back into the O2, let's say. But this can be any reaction. And this is time. This is on the horizontal axis is the progress of this reaction over time. So when we first start the reaction, there's only reactants and there's no products. So at the beginning, the forward reaction is going to be going at its maximum speed. But as the reaction goes forward, the reactants will be used up. And we know from before that reactions happen fast when there's the greatest concentrations of reactants. But the reactants are being used up, so their concentrations are going down, their amounts are going down. And so the forward rate is going to go slower and slower and slower as the reactants are used up. Now, the reverse reaction is not going at all at first because there's no products when you start the reaction. But as the reaction moves forward, you have more and more and more products, which makes the reverse reaction go faster and faster and faster. At a certain point, a lot of the reactants have been used up and some products have been made, and then the rate of the forward reaction is equal to the rate of the reverse reaction. Once that occurs, we call that equilibrium. And at that point, it appears as if the reaction is no longer going. Now, we know that's not true. Just like the boat, the level of the water in the boat stays the same, but that doesn't mean water is not still flowing in the boat. It is. And that doesn't mean we're not still dumping water out of the boat. We still are. But we're dumping it out at the same rate as going in. And here, the reaction is going forward at the same rate it's going backwards, and so there's no net change in the amount of reactants and products after that. To demonstrate that, let's look at this from a little bit different perspective. Let's say that we have this reaction which goes on in the atmosphere. Water reacts with carbon monoxide and makes hydrogen gas and CO2. So at the beginning, we've only got water and CO. And notice this is a different graph. This is talking about the concentration of water and CO over time. Okay, so at the beginning, we only have water and carbon monoxide. And so we see their concentrations are the maximum that they're going to be. And then here on the right, we have the products, hydrogen and CO2. At the beginning, we start with none of those. We don't have any of those. So let's say we mix equimolar or the same amounts in moles of CO and H2O. And they have the same concentrations, which is represented by these brackets here. And but as the reaction progresses, that concentration goes down and down and down and down. Meanwhile, while the reaction is occurring, the concentrations of the products are going up and up and up and up. Now, at a certain point, the rate at which this reaction is going forward, so let's say at the beginning, this reaction is going very quickly in the forward direction and very slowly in the reverse direction. Let's say we're right here. So we got a lot of products and a lot of reactants and very little products. So because we have very little products, the reaction is going very slowly in the reverse direction. But as the reactants get used up and we get more products, once we get to equilibrium, then the forward reaction is going the same speed as the reverse reaction. And at that point, the products are going to get used up as quickly as they're produced by the forward reaction. And so at that point, once we reach equilibrium, the reactants, there's still going to be some left. They will not get used up, but they're going to stay at the same amount because they're being used up at the same rate they're being produced from the reverse reaction. And then the products, there's been more and more products, and we have a lot of products at the end, but we're not going to get any more because now the products are going in the reverse direction, backwards, and they're making the reactants at the same speed that the reactants are making the products. So there's going to be no change in the concentration. So the question becomes, well, for every particular reaction, how much product are we going to get versus reactant? So in this reaction, when we get to equilibrium, we have a lot more product than we do reactant. This is very different from the previous, the previous example we had with the ozone. In this reaction, there's very, very little product. It's so small. See how little it is? And a lot of reactant. So this reaction does not produce a lot of products. When you're at equilibrium, you're going to have very little ozone and a lot of O2. Whereas for other reactions like this one, you'll have a lot more products than you have than reactants when you get to equilibrium. So the question is, what kind of math can we do to describe, once we get to equilibrium, how much product there is versus reactant? And that quantity that we calculate is called the equilibrium constant. And it's indicated as K with a little c. The C stands for concentration. So if we have a general reaction like this one here, where the small a, small b, small c, small d, this should be a d, these are coefficients in the balance equation, like 1, 2, 3, 4. And A, B, C, and D, these are the actual reactants and products. So the equilibrium constant is going to be the concentration of reactant to the power of its coefficient times the concentration of the, I said reactant. Start over. The concentration of products, we have the product C here, to the power of its coefficient, little c, times the concentration of the other product to its coefficient, D here. And we do this for all products, and then we divide by reactants. All products given one condition. You must only include substances that are gas or aqueous phase. You must only include substances that are in the gas or aqueous phase. The reason for this is if you have this occurring, let's say, in a jar, and we have a solid here, not all of this solid is available to react. Only what's on the surface can react. So most of this is useless. And so our amount of solid doesn't really matter. Likewise, when you have liquid, let's say you have two liquids, well, let's say we have liquid 1 and liquid 2, well, only the molecules that are on the surface of the liquid, the interface here, are available to react. And so it doesn't really make sense to include all of the amount of each liquid here, because only the molecules that are right on the edge are available to react. And so that's very different from if you have aqueous stuff. If you have aqueous, so let's say we have aqueous, well, all the particles are dissolved, so they are free to react with any other particle. If you have gases, it's the same thing, except in gas phase. All the particles are flying all around, so they're always free to interact with each other. So we only consider for the equilibrium those substances that are in the gas or aqueous phase. Solid and liquid concentrations do not change significantly during the chemical reaction. So in general, we generally have the reactants of the products, the concentration of the products divided by the concentration of the reactants. So if we have more products than reactants, we're going to get a K value that's greater than 1. Let's say our products are 2 and our reactants are 1. Then that's 2, that's greater than 1. However, if we have more reactants than products, let's say our reactants are 2 and our products are 1, well, then that is 1/2, right? And so that is less than 1. So it's greater than 1. If you have more products than reactants, you'll get a K that's greater than 1. If you have more reactants than products, you'll get a K that is less than 1. And so we can tell, if we have a measurement of the equilibrium constant, we can tell that a reaction will produce more products than reactants at equilibrium if its equilibrium constant is greater than 1. And it will have more reactants than products if the K is less than 1. So going back to our example reactions, in this reaction, we have more products, CO2 and H2, than reactants. So here, the equilibrium constant would be greater than 1. However, for this reaction, there's a lot more reactants than products. So our K here, if we were to write the K, this would be ozone, and we would square it, because the coefficient is 2, products divide by reactants, O2 to the third power. And here, if we plug this in, this is a very small number for the ozone concentration versus the oxygen concentration. We're going to get a number that is less than 1 because we have, it's going to be way, way, way less than 1 because we have way more reactants than we have products. So having more reactants than products, like in the ozone, is going to give you a K less than 1. Having more products at equilibrium than reactants is going to give you a K that is greater than 1. And so we say when there's more products at equilibrium than reactants, we say the equilibrium favors the right side of the equation, or the product side. If there are less products than reactants, we say that the reaction favors the left, or the reaction side of the molecule. So equilibrium will favor the left. So I just showed you an example of how to write a equilibrium constant. What I would like you to do is pause this video and follow my instructions and do your best. You might get it wrong, that's okay. Do your best to try to write the equilibrium constants for these reactions. Remember, we only include aqueous and gaseous reactants and products. We do not include solids like this one here or liquids. So go ahead and try these yourselves and pause now. Okay, so you've unpaused. Let's talk about what these equilibrium constants are. So here we're going to have products over reactants. So the K for this reaction is going to have products. The concentration of the HI, we're going to square that because there's a 2 for the coefficient. And that's going to be divided by the concentration of H squared to the first power, also divided by the concentration of I2 to the first power. And that's the equilibrium constant for that reaction. For reaction B, we're going to have water for our products. We put products over reactants again. It's going to be the concentration of water cubed, because there's a 3, and it's gas phase, times the concentration of nitrogen to the first power. And then we're not going to include copper here, because the copper is solid. And then it's going to be divided by reactants. So we're going to have the ammonia, NH3, and that's going to be squared. And then we don't include the copper 2 oxide because it's a solid. So here is our K for letter B. And for letter C, our K here is going to have products here, ammonia to the first power, HCl to the first power, that's our products, and our reactant is ammonium chloride solid, so there's nothing on the bottom, right? So we could just say 1 here, or we can just write it K equals ammonia concentration times HCl concentration with nothing on the bottom. And that is how you write the equilibrium constant. And again, it's products over reactants. So if you have a lot of products at equilibrium, that's going to give you a big equilibrium constant, greater than 1. If you have a lot of reactants at equilibrium and not a lot of products, that means the bottom of your fraction here is going to be bigger. So you're going to have a number that is less than 1. Now, there are ways to affect the position of the equilibrium and how much products there will be relative to reactants at any given time. We can do this by applying a change to the reaction after it has reached equilibrium and predicting what that change will be. And we can use this using a concept called Chateliers Principle. And Chateliers Principle says when a system at equilibrium is disturbed, it will react in a way that minimizes the disturbance. So the equilibrium, the reactants and products are going to react and go back to the equilibrium that they were at. And there are 3 factors that can influence the position of the equilibrium. They're the concentration of aqueous or gaseous reactants or products, the temperature, and the pressure if there are gases. So in terms of concentration, remember, If you disturb the equilibrium, the reaction is going to shift in a way that's going to fix that disturbance. So if you add in more reactants, it's going to try to consume those reactants to get back to equilibrium. If you add more products, it's going to use up those products and go backwards in the reaction to go back to the equilibrium that it was before. So if you add a product or reactant, it will be used up. If you remove one, it will be produced. So the reaction will go in the direction that will produce it. So for example, if you're making soda, if you want to make soda, you're dissolving CO2 in water and producing carbonic acid. So if we add more CO2, what will happen? When we add more CO2, the reaction is going to have to shift in a direction that will consume the added CO2 and fix this disturbance we made. So this reaction is going to shift to the left to consume the CO2 that we added. So we say that the equilibrium will shift to the left. And by adding CO2, we will cause more carbonic acid to be made. Another change that can affect the equilibrium is a change in the temperature. So when you're thinking about temperature, you need to know first whether the reaction is exothermic or endothermic. If the reaction is exothermic, we say it produces heat. So we can write heat as a product. So for example, down here, this reaction is exothermic because it is producing heat as a product, as opposed to an endothermic reaction, which requires heat. So for an endothermic reaction, you can write heat on the reactant side and say that it must be used in order to produce the products. And if we remove heat, what we're going to say is that if we lower the temperature, so lowering the temperature is like removing heat. Okay? And so it's going to move in the direction that will produce more heat. If you raise the temperature, that's like adding heat. So the reaction is going to go in the direction that will use up that additional heat. So here we are asked, what happens if the temperature drops? So that is like removing heat. So if we remove heat from this reaction by lowering the temperature, the reaction is going to have to go in the forward direction to replace the heat that is lost as we're lowering the temperature. And so this equilibrium, in this case, will shift to the right. Because this reaction is exothermic, it produces heat as a product. We are lowering the temperature, which is like removing the heat. And so when we remove the heat, the reaction will shift in the direction that will replace the heat that we have removed. And so lowering the temperature here will shift the equilibrium to the right. Finally, if you have gases in your reaction, changing the pressure of the gases will affect the reaction. And if you add pressure, add gases, this is going to, or change the volume to increase the pressure. The reaction is going to shift in the direction that will produce a lower number of moles of gases. Because remember from the ideal gas law chapter, the pressure doesn't depend on which gas it is. It only depends on how many gas molecules there are and what the temperature is and what the volume is. So by the reaction going in the direction of lowering the number of moles of gas, that will reduce the pressure. And so this will counteract the adding of pressure that we did. If we remove pressure, let's say we just make the container bigger so the pressure is lower, then the reaction will shift in a way to increase the pressure and to recover the lower pressure that you removed. So for example here, what would happen in this reaction if we increase the pressure? Well, first we need to know which direction is going to produce more moles of gas and which will produce less moles of gas. So if we count here, we have 1 mole of N2 and we have 3 moles of H2. So the total number of moles here is going to be 4 moles of gases on the left side. On the right side, we have 2 moles of NH3. So we have 2 moles of gases. So if we increase the pressure, the reaction is going to want to shift in the direction that will decrease the pressure. So that's going to be going from left to right here. This reaction, this will increase the equilibrium, or it will shift the equilibrium to the right side. And this is because we have increased the pressure. So the reaction is going to shift in the direction that will decrease the pressure back to get back to equilibrium. And that will be by going from 4 moles of gas down to 2 moles of gas, which will lower the pressure back and get us back to equilibrium. So here's an example of several changes to a particular reaction. What I want you to do is try to determine which direction each of these changes will shift the equilibrium on your own, and then unpause the video and see if you were right. Again, it's okay if you're wrong, just give it a shot. Kind of work that muscle here. So go ahead and pause the video now. Okay, please unpause. Now that you have unpaused, let's discuss the results. Here we say some methanol vapor is condensed and removed from the reaction vessel. This is the methanol here, CH3OH. So if we condense this and remove the methanol, the reaction will have to shift it to the right to replace the methanol that was removed. So this change will shift the equilibrium to the right. Now let's say that we decrease the volume in the reaction vessel. So if we decrease the volume in the reaction vessel, what that's going to do, you guys might remember P1V1 equals P2V2 from the gas laws chapter. What this says is that if we increase the pressure, the volume must go down, and if we increase the volume, the pressure must go down. So here we're increasing the volume, so that's going to result in a decrease in the we're increasing the decreasing the volume, so we're going to have an increase in pressure. So here the pressure is increasing, so to determine which direction the reaction will go, we have to count the number of moles. We have 1 mole of CO2 on the left and 2 moles of hydrogen. So we have 3 moles of gases on the left. And on the right, we have 1 mole of gases. So if we increase the pressure is increased, the equilibrium is going to have to shift in a direction that will decrease the pressure. That will be going from more moles of gas to less moles of gas. So that is going to be a shift to the right. Finally, if we increase the temperature, first of all, this reaction is an exothermic reaction. I can tell because the delta H for this reaction is negative. So this means energy is being released. So energy released, energy is released. So energy is exiting this reaction. This is exothermic. So what this means is that heat is going to be a product. So I'm going to write heat as a product here. And if I increase the temperature, that's like adding in more heat. And so the reaction is going to have to go shift to the left to get rid of some of that heat. To use it up, it's going to go backwards. So this equilibrium will shift to the left. And that's how you use Le Chatelier's principle to determine which direction the reaction will shift given certain changes. Now you may be wondering, why the heck am I learning this, right? I want to be a nurse or something, maybe, or you want to do something else. The reason is because this kind of control of equilibrium and reactions by changes in the concentrations and so forth, these are the mechanisms that your own body uses to control reactions going forwards and backwards. And these reactions, these metabolic reactions, go forwards and backwards all the time. And they're controlled by these various factors that will be explained by Le Chatelier's principle. And so that is the end of our second video for this week. I hope that was helpful. Please be sure to try all of the problems on the practice worksheet before checking the key. And have a great week. Bye-bye.